Look at the most distant galaxies we can observe. They're not behaving the way they should. Light from these ancient systems, travelling across the cosmos for billions of years, arrives at our telescopes carrying impossible information. Galaxies that shouldn't exist yet fully formed. Structures that had no time to assemble, appearing complete. Physics that breaks down exactly where our observations push against the limits of what we can see. It's as if reality itself starts malfunctioning when we look too far, too deep, too close to the beginning. Not in a poetic or metaphorical sense. Actually, measurably, observably glitching in ways that violate our most fundamental theories about how the universe works. Scientists call these anomalies. They propose modifications to cosmology, adjustments to our models, new physics to explain the discrepancies. But the problems keep multiplying. Every new telescope reveals more galaxies that shouldn't exist, more structures that violate formation timelines, more evidence that something is profoundly wrong with our understanding of reality at cosmic extremes. And the glitches aren't random. They follow patterns. They cluster at specific distances, specific epochs in cosmic history, as if there are boundaries where the rules change, where the universe transitions from one mode of operation to another. If you're ready to learn that the universe might have edges where physics fails, where reality becomes unstable, where the cosmic code starts throwing errors, subscribe and prepare yourself. What you're about to discover suggests we live in a stranger cosmos than we ever imagined. We begin. The first signs appeared in observations from the James Webb Space Telescope. This revolutionary instrument, launched in late 2021, can see farther and more clearly than any previous telescope. It peers deeper into cosmic history, observing galaxies as they existed when the universe was young, just a few 100 million years after the Big Bang. Astronomers expected to see primitive galaxies, small irregular systems still assembling themselves, the building blocks that would eventually merge into the grand spiral and elliptical galaxies we observe in the nearby universe. They expected chaos, disorder, the messy early stages of cosmic structure formation. Instead, they found galaxies that look impossible. Massive, well-organized spiral galaxies existing when the universe was supposedly too young to have produced them. These galaxies contain billions of stars arranged in orderly rotating disks, systems that should have required billions of years to assemble through gradual mergers and accretion. But the universe was less than 1 billion years old when these galaxies formed. There simply wasn't enough time for standard formation processes to produce structures this mature. The observations violated a fundamental principle of cosmology. Galaxies build up hierarchically, over time, starting small and growing through mergers. Early galaxies should be small and irregular. Only later, after billions of years of growth, should large spiral galaxies emerge. Yet here they were, large spirals existing in an epoch when they shouldn't, defying the timeline cosmology predicted. Scientists initially hoped these were rare flukes, statistical outliers that didn't fundamentally challenge the standard model. But as Webb continued observing, more impossible galaxies appeared. Dozens, then hundreds. These weren't outliers. They were common features of the early universe. Something was wrong with our models. Either galaxy formation proceeds much faster than we thought, through mechanisms we don't understand, or there's something fundamentally incorrect about how we're interpreting the observations. Some researchers proposed that the early universe was simply denser and more conducive to rapid structure formation than standard models assumed. Perhaps the first stars formed earlier, seeding galaxies sooner. Perhaps dark matter clumped more efficiently in the early universe, accelerating the assembly of visible structures. These modifications could potentially explain some observations, but they required fine-tuning parameters in ways that seemed arbitrary, adjusting the models to fit the data rather than deriving predictions from fundamental principles. And the problems extended beyond just galaxy ages. The galaxies showed other, impossible features. Some were too massive, containing more stars than should have been possible to form in the available time, even with generous assumptions about star formation rates. Others showed chemical compositions that were wrong. Stars form from gas containing hydrogen and helium from the Big Bang, plus trace amounts of heavier elements forged in previous stellar generations. Early, galaxies should contain mostly pristine primordial gas with very few heavy elements. But some early galaxies showed enrichment levels implying multiple generations of stars had already lived and died, enriching the gas with heavy elements. Again, there wasn't enough time for this to happen according to standard stellar evolution timelines. The anomalies multiplied. Quasars, supermassive black holes actively feeding on surrounding gas, appeared far earlier than they should. These black holes contain millions or billions of solar masses, requiring extensive growth periods to accumulate such mass. Standard black hole growth theory says they start as stellar remnants, perhaps a few tens of solar masses, then gradually grow by accreting gas and merging with other black holes. Growing from stellar mass to a billion solar masses should take billions of years. Yet Webb detected quasars containing billion solar mass black holes existing when the universe was less than a billion years old. These black holes would need to have grown at impossible rates, accreting matter at maximum theoretical efficiency from the moment they formed, with no breaks or slow periods. Even under optimal assumptions, the math didn't work. The black holes were too massive, too quickly. Something accelerated their growth beyond what physics allows, or they formed through entirely different mechanisms we don't understand. The pattern was clear. When we observe the universe at extreme distances, pushing toward the cosmic horizon, reality stops behaving according to established physical laws. Objects are too old, too massive, too well organized for the time available. Formation timescales are compressed impossibly. Evolution that should take billions of years happens in hundreds of millions. This isn't just a problem with our models being slightly inaccurate. This is a fundamental breakdown of our understanding of cosmic evolution. Either the laws of physics were dramatically different in the early universe, operating under entirely different rules, or we're misinterpreting what we observe in some profound way. Some cosmologists began questioning whether the standard cosmological model, the lambda CDM framework that has successfully explained so many observations, might be fundamentally flawed. Perhaps the universe didn't begin with a big bang in the way we think. Perhaps cosmic expansion doesn't work how we've modelled it. Perhaps time itself behaves differently at cosmic extremes. These are radical suggestions that most scientists are reluctant to embrace. The standard model has been incredibly successful. It explains the cosmic microwave background radiation, the large-scale structure of the universe, the abundance of light elements, and countless other observations. Abandoning it requires extraordinary justification. But the anomalies from the universe's edge are accumulating to the point where ignoring them becomes harder than confronting them. Each new observation adds to the pile of discrepancies. Each discovery strains the standard model further. The universe appears to be telling us something important. When we look to the edges of observable space, to the earliest moments of cosmic history accessible to our telescopes, reality doesn't follow the rules we've established. It glitches, behaving in ways that shouldn't be possible, revealing either gaps in our understanding or fundamental limitations on how far our physical theories can be extrapolated. We've reached a boundary, not a physical edge to space, but a conceptual edge to our understanding. Beyond this boundary, the familiar physics that works so well in our local cosmic neighbourhood breaks down. Galaxies form too quickly, black holes grow too fast, structures assemble on impossibly short timescales. This is the glitching of reality at the edge of the universe, and it's forcing cosmology into a crisis that might fundamentally reshape our understanding of cosmic history and the nature of reality itself. There's something deeply wrong with how light behaves when it travels across cosmic distances. The farther away an object is, the more its light should be redshifted, stretched to longer wavelengths by the expansion of space. This relationship is one of the most fundamental tools in cosmology, allowing us to measure distances and determine how long ago we're seeing distant objects. But recent observations reveal systematic discrepancies. Objects at extreme distances sometimes show redshifts that don't match their expected distances based on other indicators. The relationship between redshift and distance, which should be smooth and predictable, shows irregularities that hint at something wrong with either our understanding of cosmic expansion or the nature of light propagation across the universe. The problem emerged from precise measurements of very distant galaxies. Astronomers use multiple methods to estimate distances: brightness of standard candles like supernovae, sizes of standard rulers like galaxy clusters, gravitational lensing effects. These methods should agree with each other and with distances calculated from redshift. They don't always agree. Some galaxies show redshifts indicating they're at one distance, while their brightness or angular size indicates a different distance. The discrepancies aren't huge, typically a few percent, but they're systematic and significant. In nearby galaxies, the measurements agree beautifully, but at extreme distances, approaching the observable universe's edge, the methods diverge. It's as if different distance indicators are measuring different things, or as if the relationship between redshift and distance breaks down at cosmic extremes. One possibility: cosmic expansion isn't as smooth as we assume. The Standard Model treats expansion as happening uniformly throughout space, with the expansion rate varying only with time as the universe ages. But perhaps expansion is lumpy, varying from place to place depending on local matter, density, or other factors. If we're in a region where expansion is slightly faster or slower than average, it would affect how we interpret redshifts. Light travelling from distant galaxies would be stretched by expansion at different rates depending on what regions of space it passes through. This could create systematic offsets between redshift-based distances and other distance measures. Galaxies at similar actual distances might show different redshifts depending on what path their light took through varying expansion regions. Testing this requires mapping the expansion rate across the universe, looking for variations that correlate with structure. Some studies claim to find such variations, but the evidence is controversial and difficult to confirm. Another possibility involves the nature of light itself. We assume light travels through the vacuum of space without losing energy or changing wavelength except through interactions with matter or the expansion of space. But perhaps over extreme distances, other effects become significant. Photons might interact with quantum fields pervading space, losing tiny amounts of energy in each interaction. Over billions of light years, these losses could accumulate, creating additional redshift beyond what expansion produces. This tired light hypothesis was popular decades ago, but fell out of favour because it couldn't explain other observations. However, modern versions propose quantum field interactions that weren't considered in the original tired light theories. If these interactions exist, they'd be undetectable over short distances, but might become measurable over cosmic scales. The problem is that any such interaction that affects light should also affect other particles and fields in detectable ways. If photons lose energy to quantum fields, we should see signatures of this in other observations. So far, we don't, which argues against tired light explanations. There's also the possibility that our basic cosmological framework is wrong. The Standard Model assumes a specific history of cosmic expansion, rapid inflation in the first moments, then gradual deceleration as matter's gravity slows expansion, then recent acceleration, driven by dark energy. This history is inferred from observations of the cosmic microwave background, supernova distances, and other data. But if any of these observations are being misinterpreted, the inferred expansion history could be wrong. Some alternative cosmologies propose different expansion histories that produce different relationships between redshift and distance. In these models, objects at extreme distances might show redshifts that differ from standard predictions, potentially explaining the observed discrepancies. The challenge is that alternative. Cosmologies typically struggle to explain other observations as well as the Standard Model does. They might resolve the redshift crisis, but fail to account for the cosmic microwave background patterns or the abundance of light elements formed in the Big Bang. Scientists are caught between accepting observations that contradict the Standard Model and abandoning a framework that successfully explains so much else. Neither option is attractive. The redshift crisis also connects to another anomaly, the Hubble tension. Measurements of the current cosmic expansion rate, the Hubble constant, give different values depending on whether you measure it using nearby supernovae or distant cosmic microwave background radiation. The nearby measurements consistently give higher values than the distant measurements. This shouldn't happen if our cosmological model is correct. The discrepancy has persisted through years of increasingly precise observations. Some researchers think the redshift anomalies and the Hubble tension are related, both symptoms of a deeper problem with our understanding of cosmic expansion. Perhaps the expansion rate varies in ways we haven't accounted for. Perhaps our distance measurements are systematically biased at certain scales. Or perhaps we're seeing evidence of new physics, a modification to general relativity that becomes significant at cosmic scales, or a property of dark energy we haven't recognized. The crisis has spawned hundreds of theoretical papers proposing solutions. Some invoke additional dark energy components with exotic properties. Others modify gravity on large scales. A few suggest we're misinterpreting the cosmic microwave background data. None of the proposals are fully satisfactory. They all require either fine-tuning parameters to match observations or making predictions that conflict with other measurements. The community is searching for a modification that resolves multiple anomalies simultaneously without creating new problems. What makes this particularly troubling is that redshift is foundational to cosmology. Almost everything we know about the distant universe comes from analysing redshifts. If our interpretation of redshift is even slightly wrong, it cascades through every calculation, affecting distance estimates, age calculations, and expansion rate measurements. The glitching at reality's edge might be telling us that redshift doesn't mean what we think it means when applied to extreme distances. Perhaps the simple relationship between redshift and recession velocity breaks down at cosmic scales. Perhaps light's journey across the universe involves processes we haven't accounted for. This uncertainty affects our most basic claims about the universe. How big is the observable universe? How old are the most distant galaxies? When did the first stars form? All of these depend on correctly interpreting redshift. If redshift is misbehaving at extreme distances, we can't trust our answers to these questions. The cosmic timeline might be different from what we've calculated. Distances might be larger or smaller than we think. The universe's age might require revision. Scientists are working to resolve this crisis through better observations and more sophisticated models. New telescopes are measuring redshifts with unprecedented precision. Theoretical frameworks are being refined to account for possible complications. But resolution might require abandoning cherished assumptions. We might have to accept that the universe is stranger at its edges than our theories predict, that the smooth, predictable cosmology we've constructed breaks down when pushed to extremes. The missing redshift crisis is a symptom of reality glitching, the universe behaving inconsistently with established physical law when observed at maximum distances. And it's just one of several anomalies suggesting that something fundamental goes wrong when we look toward the cosmic horizon. The universe should be lumpy, but not too lumpy. There are limits on how large structures can grow in the time available since the Big Bang. These limits come from fundamental physics. Gravity pulls matter together, but cosmic expansion works against it. The balance determines how quickly structures form and how large they can become. Theory predicts maximum structure sizes at different cosmic epochs. Early in the universe, structures should be small. As time passes, they grow through gravitational attraction and mergers. The largest structures we observe should reflect the age of the universe and the strength of gravity. Except that's not what we see. Astronomers keep discovering structures that violate these size limits. Objects so vast they shouldn't have had time to assemble. Arrangements of matter that require longer to form than the universe has existed. The discoveries began with large quasar groups, clusters of these brilliant objects spanning hundreds of millions of light years. Individual quasars are already problematic, as discussed earlier, being too massive too early. But finding them clustered in enormous groups compounds the problem. For quasars to cluster, they must be embedded in a large-scale structure of dark matter in galaxies. Such structures form hierarchically over billions of years as smaller structures merge. The time required scales with size. Larger structures need more time. Some observed quasar groups span distances so vast that standard structure formation theory says they couldn't have assembled in the time available. They violate theoretical size limits by factors of 2 or more. Scientists call these violations crisis-level discrepancies because they challenge the foundations of structure formation theory. The observations aren't marginal or questionable. They're clear detections of structures that simply shouldn't exist according to our best models. Then came the discovery of even larger structures. The Hercules Corona Borealis Great Wall, a filament of galaxies stretching across billions of light years, is so enormous that light takes 10 billion years to cross it. This structure appears to have formed when the universe was only a few billion years old. The physics problem is clear. How does matter organize into a structure spanning 10 billion light years in just a few billion years? Gravity propagates at the speed of light. Information about matter distribution can't travel faster than light. For matter to organize into such vast structures, requires time for gravitational signals to cross the distances involved. The timescales don't work. The structure is too large for its age. Either it formed through processes we don't understand, or our dating of when it formed is wrong, or our size measurements are wrong, or fundamental physics needs modification. Each possibility has problems. Unknown formation processes require abandoning established structure formation theory without a replacement. Wrong dating would require systematic errors in redshift interpretation. Wrong sizes would require distance measurement errors. Modified physics requires overturning general relativity or our understanding of gravity. The community has explored all these possibilities without finding satisfactory solutions. The structures remain impossible according to standard cosmology, yet they observably exist. There's also a statistical problem. Large structures are rare by definition. There aren't many regions of the universe big enough to contain billion light-year structures. The probability of finding even one structure near the theoretical size limit is low. Finding multiple structures that violate the limits is extremely improbable, yet we've found several. This suggests the violations aren't statistical flukes, but indicators of systematic problems with our models. Some researchers propose that the early universe had unusual density fluctuations that seeded these structures. If the primordial density variations were larger than standard inflation theory predicts, large structures could form faster. But this creates a new problem. The cosmic microwave background radiation shows us the density variations in the early universe. They're not large enough to seed the observed structures quickly. Any modification that increases primordial fluctuations conflicts with microwave background observations. Others suggest modified gravity theories where gravitational attraction is stronger on large scales than general relativity predicts. Stronger gravity could pull structures together faster, allowing impossible structures to form in the available time. This approach has its own difficulties. Modified gravity theories struggle to match solar system tests and other local gravity measurements while also explaining cosmic structure. The modifications that work on cosmic scales often fail locally. There's also the possibility that large structures are optical illusions, chance alignments of unrelated objects that appear connected but aren't actually gravitationally bound structures. If several independent filaments happen to align along our line of sight, they might appear as one enormous structure. This explanation works for some cases, but not all. The largest structures show evidence of physical connection, not just visual alignment. Galaxies within them share similar velocities and appear to be gravitationally interacting. The impossible structures crisis suggests that either structure formation proceeds through mechanisms we don't understand, or the universe's age and expansion history are different from standard cosmology assumes, or observational selection effects are making rare statistical flukes appear common. None of these explanations is satisfying. Each requires abandoning or significantly modifying established theory without clear guidance about what should replace it. What's particularly disturbing is that the impossible structures appear at specific cosmic distances and epochs. They cluster near the edge of the observable universe. In the early cosmic era, when the standard model already struggles to explain rapid galaxy and black hole formation. It's as if there's a regime, the first few billion years of cosmic history, the most distant reaches we can observe, where different rules apply. Standard physics and standard structure formation work well in the nearby universe and in later epochs, but push toward the edge, toward the beginning, and reality starts glitching. Structures form impossibly quickly. They reach impossible sizes. They violate theoretical limits by comfortable margins, not edge cases that might be explained by rare fluctuations. This pattern suggests the glitching isn't random. It's systematic, indicating a regime where our theories fail rather than isolated anomalies that could be explained away. The crisis is ongoing. New telescopes continue discovering impossible structures. Each discovery is met with attempts to explain it within existing frameworks, followed by eventual recognition that standard explanations don't work. The astronomical community is increasingly uncomfortable with the accumulating violations. Papers discussing crisis-level discrepancies are becoming common. Cosmology conferences devote sessions to the impossible structure problem, but there's no consensus on solutions. The field is fragmented, with different groups pursuing incompatible approaches. modified gravity, alternative cosmologies, new structure formation mechanisms, systematic observational biases. What's clear is that something is profoundly wrong with our understanding of how large-scale structure forms in the universe. The observations are forcing us toward conclusions that challenge the foundations of modern cosmology, and the impossible structures are just one aspect of the larger pattern of reality glitching at the universe's edge. Combined with impossible galaxies, impossible black holes, and redshift anomalies, they paint a picture of a cosmos that stops following familiar rules when observed at extreme distances and times. The universe's edge is not just far away, it's different. And that difference might be telling us something fundamental about the limits of our physical theories or about the nature of cosmic reality itself. According to general relativity, time should run slower in regions of high gravity and in reference frames moving at high velocities relative to us. This time dilation is one of relativity's most precisely tested predictions. It's verified in GPS satellites, particle accelerators, and countless other experiments. At cosmic scales, time dilation should affect how we observe distant events. Light from distant galaxies shows us those galaxies as they existed billions of years ago. But because the universe was denser in the past, and because distant galaxies are receding from us at substantial fractions of light speed, time should have run differently in those galaxies compared to here. Specifically, processes in distant galaxies should appear slowed down when we observe them. Supernovae should evolve more slowly. Variable stars should pulse with stretched periods. Any periodic or time-dependent phenomenon should show measurable time dilation that increases with distance. And we do observe this for supernovae. Type 1, A supernovae, used as standard candles to measure cosmic distances, show characteristic light curves, brightness rising then fading over specific timescales. Distant supernovae show stretched light curves consistent with time dilation predictions. This is considered a major confirmation of relativistic cosmology. The observations match theoretical predictions precisely. Except for quasars, these objects should also show time dilation. Their brightness varies chaotically over timescales ranging from days to years. If time dilation affects distant quasars, their variability timescales should stretch proportionally with distance. They don't. Multiple studies have searched for this effect. The results are controversial, but many analyses find that quasar variability timescales don't show the expected time dilation. Distant quasars vary on the same timescales as nearby ones, not the stretched timescales relativity predicts. This is deeply problematic. If time dilation affects supernovae but not quasars, something is wrong. Either one of these observations is being misinterpreted, or different physical processes obey different time dilation rules, which makes no sense. Some astronomers argue the quasar results are affected by selection effects. Perhaps we preferentially detect distant quasars that happen to vary on shorter timescales, biasing the sample in ways that mask time dilation. Others propose that quasar variability is driven by processes that don't scale simply with time. Maybe the accretion disk dynamics that cause quasar flickering involve feedback mechanisms that compensate for time dilation, maintaining similar variability timescales regardless of distance. These explanations require specific assumptions about quasar physics that are difficult to test independently. They seem designed to preserve time dilation rather than being derived from fundamental understanding of how quasars work. The alternative is disturbing. Time dilation might not apply uniformly across cosmic distances. Perhaps relativity breaks down at extreme distances, or perhaps our interpretation of what we're observing is fundamentally flawed. There's another time-related anomaly. The early universe should have evolved rapidly from our perspective. Events that took millions of years in the early universe's reference frame should appear compressed to much shorter durations when we observe them billions of years later. This effect combines cosmological redshift and time dilation in complex ways. But the bottom line is that processes in the early universe should appear to happen faster from our observational perspective than similar processes in the nearby universe. Some observations match this prediction, but others don't. The rapid formation of impossible galaxies and black holes mentioned earlier involves time paradoxes. Not only are these objects too mature for their age, but the processes that built them appear to have occurred impossibly quickly, even accounting for time dilation. It's as if time ran faster in the early universe than relativity predicts, or as if processes accelerated beyond what physical mechanisms can achieve, even with favourable time dilation. This connects to the redshift crisis discussed earlier. If our interpretation of redshift is wrong, our calculations of time dilation are also wrong. The two effects are intimately linked through the same cosmological framework. The time dilation paradoxes suggest either that relativity fails at cosmic scales, or that we're systematically misunderstanding something fundamental about how we observe the distant universe. Some theorists have proposed that time itself might behave differently in different cosmic epochs. Perhaps the rate at which physical processes occur varied throughout cosmic history in ways beyond what standard relativity predicts. This would require modifications to general relativity or additional physics that affects how time flows. Such modifications are highly speculative and typically struggle to match local experimental tests of relativity while also explaining cosmic anomalies. There's also the quantum gravity consideration. General relativity is a classical theory that might break down at extreme energies or on very small scales where quantum effects become important. Most physicists expect this breakdown to occur at the Planck scale, energy and distance scales so extreme they're completely inaccessible to direct observation. But perhaps quantum gravity effects become relevant at cosmic scales in ways we haven't anticipated. Maybe the fabric of space-time itself behaves differently when integrated over cosmic distances, affecting how time dilation accumulates. This is highly speculative, but the time dilation paradoxes are strange enough that exotic explanations can't be dismissed without consideration. What makes the situation particularly confusing is that time dilation works perfectly in some contexts. Supernovae, gravitational lensing time delays, certain pulsar observations, but appears to fail in others, specifically quasar variability. This inconsistency is harder to explain than a uniform failure would be. If time dilation simply didn't work at cosmic scales, we'd see discrepancies across all observations. But we don't. Some phenomena match predictions perfectly, while others show no effect at all. This suggests the problem might not be with time dilation itself, but with how we're interpreting specific observations. Perhaps quasar variability is driven by processes we don't understand that happen to mimic the absence of time dilation. Or perhaps there are selection effects, observational biases, or systematic errors in how we analyse the data that create false impressions of anomalies. Resolving these paradoxes requires either better observations that can definitively measure time dilation in distant quasars, or better theoretical understanding of what causes quasar variability and how it should behave at different redshifts. Neither is easy. Quasars are complex, chaotic systems whose behaviour is difficult to model from first principles, and detecting subtle time dilation effects requires large statistical samples and careful control of systematic errors. The time dilation paradoxes represent another aspect of reality glitching at the universe's edge. Time itself seems to behave inconsistently when we observe extreme distances, following predictions in some cases but not others, creating patterns that challenge our understanding of relativistic cosmology. Combined with impossible structures, impossible galaxies, and redshift anomalies, the time dilation paradoxes contribute to a growing sense that something fundamental is wrong with how we model the distant universe. Whether the solution involves modified physics, better understanding of astrophysical processes, or recognition of systematic, observational errors remains unclear. What is clear is that our current framework struggles to coherently explain all the observations we're making at the universe's edge. The cosmic microwave background radiation should be isotropic, the same in all directions, except for tiny random fluctuations reflecting quantum variations in the early universe. This isotropy is a cornerstone prediction of standard cosmology. The universe should have no preferred directions. Physics should be the same everywhere. But it's not. The cosmic microwave background shows large-scale patterns that align with each other and with our solar system's geometry in ways that are statistically impossible if the universe is truly isotropic. Scientists call this the axis of evil, a somewhat tongue-in-cheek name for a genuinely disturbing pattern in the data. The lowest multipole moments of the microwave background, the largest scale patterns, align along a specific axis through space. This axis correlates suspiciously with the plane of Earth's orbit around the Sun. This shouldn't happen. The early universe had no knowledge of where Earth would be or how its orbit would be oriented. The microwave background formed nearly 14 billion years ago, when the universe was uniformly filled with hot plasma. Earth didn't exist. The solar system didn't exist. Nothing about that early epoch should correlate with our local geometry. Yet the correlation exists. Multiple independent analyses confirm it. The pattern is not a data processing artifact or an error in telescope calibration. It's real structure in the microwave background that aligns with our local reference frame. One possibility, pure coincidence. With enough patterns to look for, eventually you'll find correlations that seem meaningful, but aren't. The axis of evil might be a statistical fluke, one of those rare occurrences that happen occasionally in any large data set. But the probability is very low. Statistical analyses suggest less than 1% chance that the observed alignment is random. That's not conclusive evidence against coincidence. Unlikely things happen, but it's uncomfortable. Another possibility, systematic error. Perhaps our telescopes or data analysis methods introduce artificial patterns that correlate with how we observe the sky. Maybe there's a subtle bias in how we remove foreground contamination from our galaxy's emission. Extensive efforts to check for such errors haven't found any. The axis of evil persists across different satellite missions, different analysis techniques, different researchers. If it's an artifact, it's a remarkably robust one that survives every attempt to eliminate it. The disturbing alternative? The universe actually has a preferred direction. The cosmos is not perfectly isotropic. There are large-scale asymmetries that break the cosmological principle. The assumption that the universe looks the same from every location and in every direction. This would overturn a century of cosmological thinking. The cosmological principle isn't just a nice idea. It's foundational to how we model the universe's evolution. If the universe has preferred directions, our equations need modification. Predictions change. The entire framework becomes more complex and less predictive. Some theorists have proposed explanations involving cosmic topology. Maybe the universe is finite and has unusual geometry that creates preferred directions. If space wraps around on itself in specific ways, it could create patterns in the microwave background that appear as alignments. Testing this requires looking for repeating patterns in the sky, images of the same structures appearing in different directions because light has wrapped around the universe. No such repetitions have been confirmed, which argues against simple topological explanations. Others invoke inflationary physics. The rapid exponential expansion in the universe's first moments is thought to have smoothed out any initial irregularities. But perhaps inflation was incomplete or directional, preserving or even creating large-scale asymmetries. This would require specific modifications to inflation theory, fine-tuning the inflationary potential or initial conditions in ways that seem arbitrary. You can construct models that produce the axis of evil, but they feel designed to fit the observations rather than arising naturally from fundamental principles. There's also a connection to dark flow, another anomalous observation. Clusters of galaxies appear to show coherent large-scale motion in a specific direction beyond what standard cosmology predicts. This dark flow aligns roughly with the axis of evil. If both anomalies are real and related, they suggest the universe has a large-scale structure that extends beyond the observable universe. Perhaps we're in a region that's being pulled towards some enormous mass concentration beyond our cosmic horizon. This would explain the aligned patterns. Both the microwave background asymmetries and galaxy motions reflect the same large-scale gravitational influence from beyond what we can observe. But dark flow observations are controversial. Different studies get different results. Some find strong evidence for the effect, others find none. The reality of dark flow remains contested. The axis of evil also relates to anomalies in the microwave background's overall pattern. The quadrupole and octopole moments, specific mathematical modes in the temperature fluctuation pattern, are weaker than standard inflation predicts. This suppression of large-scale power is another problem for cosmology. Inflation should produce a specific spectrum of fluctuations with predictable relative amplitudes. The observed spectrum matches predictions on small and medium scales but deviates on the largest scales. Combined with the axis alignment, this suggests something unusual about the universe's largest scale properties. Either the early universe was not as uniform as we assume, or our observations are affected by something we haven't accounted for, or physics operates differently on the largest observable scales. Some researchers suggest the anomalies might be telling us about the geometry of the entire universe. If space has very slight curvature, too slight to detect through distance measurements, it could affect the largest scale modes of the microwave background while leaving smaller scales unchanged. But this requires the curvature to be precisely tuned to affect only the specific scales where anomalies are observed. Such fine-tuning is possible, but unsatisfying theoretically. The axis of evil represents reality glitching on the largest observable scales. The universe shows patterns where it should show randomness, alignments where there should be independence, correlations that violate our most fundamental assumptions about cosmic isotropy. This is different from the glitches at the universe's edge in time, the impossible galaxies and structures. This is a glitch in the universe's spatial distribution at the largest scales, a breakdown of isotropy that shouldn't exist according to everything we think we understand about cosmology. Some researchers dismiss the axis of evil as a distraction, a statistical anomaly that will disappear with better data or better analysis. But others see it as a crucial clue that our cosmological framework is incomplete. The fact that multiple large-scale anomalies, the axis of evil, suppressed quadrupole power, possible dark flow, all point towards similar preferred directions, suggests these aren't independent statistical flukes. They might be different manifestations of the same underlying phenomenon. What that phenomenon is remains unknown, but its existence challenges the cosmological principle that has guided our thinking for a century. And combined with all the other glitches appearing at various cosmic extremes, it adds to the growing sense that reality doesn't behave as our theories predict when pushed to the limits of observability. Quantum mechanics governs the microscopic world. General relativity governs the macroscopic cosmos. These two theories are incompatible at a fundamental level, and physicists have struggled for decades to reconcile them into a unified theory of quantum gravity. Most expect this reconciliation to matter only at extreme conditions, inside black holes, at the Big Bang, in the first moments of cosmic inflation. The energy and density scales where quantum gravity becomes relevant should be completely inaccessible to normal observation, but strange observations at the universe's edge suggest quantum effects might manifest at cosmic scales in unexpected ways. The boundary between quantum and classical physics might not be where we think it is. Start with the problem of initial conditions. The cosmic microwave background shows us density fluctuations from the early universe that seeded all cosmic structure. These fluctuations are thought to originate from quantum fluctuations during inflation, microscopic quantum variations that got stretched to cosmic scales by exponential expansion. This explanation requires quantum mechanics to operate meaningfully at scales far larger than atoms, creating correlations across regions that will eventually become separated by billions of light years. It's already a strange extrapolation of quantum theory into regimes where we don't fully understand if it should apply. But the observed fluctuation pattern shows anomalies that standard quantum inflation doesn't predict. Beyond the large-scale issues already discussed, there are features in the fine-scale pattern that don't match expectations from simple quantum fluctuations. Some of these features look more ordered, less random than quantum fluctuations should be. Others show correlations across scales that shouldn't be correlated if the fluctuations were generated by independent quantum processes. These anomalies might indicate that quantum mechanics work differently during inflation than it works in laboratory conditions. Or they might suggest that the fluctuations weren't entirely quantum in origin, that classical processes or unknown physics contributed. Either possibility is disturbing. Quantum mechanics is supposed to be universal, working the same way everywhere. If it operated differently in the early universe, we need to understand why and what conditions triggered the different behaviour. Then there's the measurement problem at cosmic scales. In quantum mechanics, systems exist in superpositions until measured. Measurement causes wave function collapse, forcing the system into a definite state. But what constitutes measurement at cosmic scales? The early universe was a quantum system evolving according to quantum equations. When did it transition from quantum to classical? What measured the quantum fluctuations, causing them to collapse into the definite density variations we observe. Standard inflation theory doesn't have a clean answer. It invokes decoherence, the idea that interactions with the environment cause quantum systems to behave classically. But in the early universe, everything was the environment. There was no external system to decohere anything. Some theorists propose that gravity itself acts as a measurement device, that quantum fluctuations decohere when they interact with gravitational fields. This is speculative and controversial, but it's an attempt to solve the problem of how quantum fluctuations became classical structure. The issue becomes more acute when considering the universe as a whole. If the universe is a quantum system, its wave function should describe all possible states simultaneously. But we observe one specific state, one particular outcome of cosmic evolution. What collapsed the universe's wave function? The question sounds metaphysical, but it has physical implications. If quantum mechanics applies to the entire cosmos, we need to understand how the cosmos transitions from quantum possibility to classical reality. There are also quantum effects that might operate on unexpectedly large scales. Quantum entanglement, where particles remain correlated regardless of distance, could potentially link regions of the early universe that later became separated by cosmic expansion. Some researchers have looked for signatures of quantum entanglement in the cosmic microwave background. The idea is that if regions of the early universe were quantum entangled, their temperature fluctuations might show correlations that can't be explained by classical physics. Claims of detecting such correlations have been made but remain controversial. The patterns could have classical explanations, or they could be artifacts of how the analysis was performed. But if confirmed, they would indicate that quantum effects persist on cosmological scales in observable ways. There's also the vacuum energy problem. Quantum field theory predicts that empty space should have an enormous energy density due to virtual particle fluctuations in the quantum vacuum. Calculating this energy density gives a value that's larger than observed dark energy by a factor of more than 100 orders of magnitude. This is the worst prediction in physics. Something is catastrophically wrong with either our calculation of vacuum energy or our understanding of how it affects cosmic expansion. The discrepancy is so severe that explaining it might require entirely new physics. One possibility is that quantum field theory breaks down at large scales. The virtual particle fluctuations that produce vacuum energy in quantum calculations might not actually exist, or might cancel out through mechanisms we don't understand when integrated over cosmic volumes. This would mean that quantum field theory, spectacularly successful at describing particle physics, fails when applied to the universe as a whole. It would be valid locally, but not globally, suggesting a fundamental limit to how far quantum concepts can be extrapolated. Another quantum-related mystery involves the arrow of time. The second law of thermodynamics says entropy always increases, giving time a direction. But the fundamental laws of physics are time-symmetric. They work the same forward and backward. The asymmetry must come from initial conditions. The early universe had extremely low entropy, and everything since then has been entropy increasing as the universe evolves toward equilibrium. But why did the universe start with low entropy? This is a profound puzzle. In quantum mechanics, the initial state of any system is arbitrary, not derived from deeper principles. The universe's initial low entropy state seems to require explanation, yet we have none. Some cosmologists propose that quantum mechanics at cosmic scales might have features that prefer low entropy initial states. Perhaps there's a quantum selection effect that makes low entropy universes more likely to exist or be observed. This ventures into speculative territory involving quantum cosmology and the anthropic principle. But the mystery is real. We don't understand why the universe's quantum initial state had the specific low entropy character required for structure formation and the arrow of time. There are also suggestions that quantum effects might become relevant again at very late cosmic times. As the universe expands and cools toward eventual heat death, the characteristic energy scales drop. Eventually, they might drop low enough that quantum effects start dominating over classical evolution. In this far future, the universe might undergo quantum phase transitions, tunneling events, or vacuum decay processes that don't occur in the current classical dominated era. Reality might become quantum again, though in ways very different from the quantum early universe. These late-time quantum effects are highly speculative and won't occur for unimaginably long timescales if they occur at all. But they illustrate how quantum physics might bookend cosmic history, relevant at the beginning and perhaps at the end, with a classical era in between. The quantum breakdown at cosmic scales represents a conceptual glitch in our understanding. We know quantum mechanics governs the microscopic world. We know general relativity governs cosmic scales, but we don't know how to consistently apply quantum concepts to the entire universe, or what happens when we try. The anomalies in the cosmic microwave background, the measurement problem for cosmic wave functions, the vacuum energy disaster, the entropy puzzle, all of these hint that quantum mechanics might not work at cosmic scales the way it works in laboratories. Perhaps quantum mechanics is an approximation that breaks down when applied to systems as large as the universe. Perhaps it requires modification or completion by theories we haven't discovered. Perhaps the universe is fundamentally classical, and quantum mechanics is an emergent phenomenon that applies only to small subsystems. These are deep questions without clear answers. But the fact that we're forced to ask them, that observations are pushing us toward conclusions that challenge our quantum mechanical framework, suggests reality is glitching when we try to apply our most successful microscopic theory to the cosmos as a whole. Some of the glitches at reality's edge resemble exactly what you'd expect if the universe were a simulation with finite computational resources. This is an uncomfortable observation that most scientists avoid discussing publicly, but privately some acknowledge the patterns are suggestive. A simulation would need to conserve computational resources. You couldn't simulate every particle everywhere at maximum resolution. You'd use shortcuts, approximations, rendering only what's observed in detail while keeping everything else abstract. This would create observable signatures, resolution limits below which physics changes behavior, boundary conditions at the edge of the simulated volume where things stop behaving consistently, glitches when the simulation is pushed beyond its designed parameters. The universe shows several features consistent with this picture, though every feature has conventional explanations as well. The question is whether the pattern of multiple simulation-like features is coincidental or meaningful. Start with quantum mechanics itself. The uncertainty principle prevents precise, simultaneous knowledge of position and momentum. The universe literally doesn't have definite values for these quantities until measurement forces it to choose. This is exactly how you design a simulation to conserve resources. Don't calculate exact particle trajectories until something needs to know them. Keep everything as probability distributions, computationally cheaper than tracking definite states. When observation forces calculation of a definite value, the wave function collapses. The simulation commits to a specific outcome, updating its state from probable to actual. This interpretation of quantum mechanics, the simulation hypothesis version, is empirically identical to standard interpretations, but philosophically quite different. Then there's the Planck scale, the smallest meaningful length and time in physics. Below these scales, space and time become quantum, and our equations break down. Many physicists expect that space-time itself is discrete at the Planck scale, made of indivisible units like pixels on a screen. This looks like resolution limits in a simulation. The Planck scale would be the simulation's fundamental grid spacing, the smallest unit that's actually computed. Trying to probe below this scale is like trying to see individual pixels in a digital image by zooming in. Eventually you hit a limit where the underlying discrete structure becomes apparent. We can't directly observe the Planck scale, it's far too small. But theoretical arguments suggest space and time are discrete at this level. If true, it means the universe has a minimum resolution, exactly what a simulated reality would require. The speed of light also fits this picture. Information can't travel faster than light, which limits how quickly different parts of the simulation need to update each other. Light speed could be the simulation's refresh rate, the maximum speed at which information propagates through the computational substrate. This explains why light speed is constant and why nothing can exceed it. It's not a speed limit on motion through space, it's a limit on information, propagation through the simulation. Everything respects this limit because it's fundamental to how the simulation operates. The holographic principle adds another simulation-like feature. This principle says that all information in a volume of space can be encoded on its boundary surface. The information content scales with surface area, not volume. This is weird from a physical perspective. Why should three-dimensional volume be described by two-dimensional surfaces? But it makes perfect sense for a simulation. Simulating volume is expensive. Simulating surfaces is cheaper. If you can encode all volumetric information on boundaries, you dramatically reduce computational costs. Black holes demonstrate the holographic principle explicitly. Their entropy, the information they contain, is proportional to their surface area, not their volume. The universe seems to be telling us that information is fundamentally two-dimensional, stored on surfaces, with three-dimensional volume being an emergent phenomenon. Now consider the glitches at the universe's edge. Impossible galaxies forming too quickly, structures too large for their age, redshift anomalies, time dilation paradoxes, the axis of evil showing preferred directions. These problems cluster at the observable universe's edge. At the maximum distance and look-back time, we can observe. It's as if the simulation has boundary conditions where it transitions from detailed rendering to lower resolution, or where it stops bothering to maintain full consistency. In a simulated universe, you'd put maximum effort into the observed region where intelligent beings can make measurements. Farther away, in regions barely observable, you might relax constraints, use approximations, allow inconsistencies that wouldn't be noticed except through sophisticated analysis. The concentration of anomalies near observational limits is exactly what this predicts. The universe behaves normally in well-observed regions where inconsistencies would be obvious. It glitches at the edges where observations are difficult and ambiguous. You could argue that all these features have conventional physical explanations. Quantum mechanics is just how nature works, not evidence of simulation. The Planck scale emerges from quantum gravity, not computational limits. Light speed is a feature of space-time geometry, not refresh rate. These conventional explanations are perfectly valid. The simulation hypothesis doesn't make unique predictions that distinguish it from standard physics. Any observation can be explained either way. But the pattern, multiple features that would make sense in a simulation, all present in the actual universe, is at least suggestive. It's not proof, it's not even strong evidence, but it's an interesting coincidence if coincidence is all it is. Some physicists have proposed ways to test the simulation hypothesis. Look for computational errors that slip through, inconsistencies in physical laws, glitches in conservation laws, numerical precision limits in physical constants. Others suggest searching for evidence of patches or updates, moments when the simulation was modified to fix problems or add features. These would appear as discontinuities in physical law or sudden changes in observed phenomena. So far, no such evidence has been found. The universe appears consistent with its own rules across all accessible observations. If it's a simulation, it's a very good one that doesn't make obvious errors. The simulation hypothesis also predicts that we might be able to detect the computational substrate if we look carefully enough. Perhaps dark matter is a computational artifact, code objects that have gravitational effects but no other interactions. Perhaps dark energy is memory overflow, the simulation running out of resources and using a constant background term to approximate what should be detailed calculations. These are wild speculations with no empirical support, but they show how simulation thinking can reframe cosmological mysteries. What seems like fundamental physics from one perspective looks like implementation details from another. The philosophical implications are profound. If we're in a simulation, what's real? Are we conscious or just simulated consciousness? Does our universe have objective existence, or is it information in some external computer? These questions have no testable answers. Whether you're in base reality or a simulation, your experiences are identical. The simulation hypothesis doesn't change how you should live or what you should value, but it does change the meaning of reality glitching at the universe's edge. If the glitches are simulation artifacts, they're not telling us about fundamental physics. They're telling us about the limitations of the computational system running our universe. This interpretation is not mainstream science. Most cosmologists work within conventional frameworks and prefer physical explanations for anomalies over simulation speculation. But the simulation hypothesis persists as an alternative way of thinking about why reality might behave strangely at extremes. Whether the glitches are simulation artifacts or physics we don't yet understand, they're forcing us to question our most basic assumptions about reality. And that questioning, regardless of answers, is valuable for pushing our understanding forward. After examining glitches in galaxy formation, structure growth, redshift relationships, time dilation, cosmic isotropy, quantum mechanics, and possible simulation signatures, a pattern emerges. Reality doesn't fail uniformly. It glitches specifically at boundaries, the edge of the observable universe, the earliest cosmic epochs, the largest observable scales, the smallest quantum scales. These boundaries might not be features of the universe itself. They might be limits of our ability to observe and understand. We're pushing against the edges of what's knowable from our position in space and time. And what we find there is ambiguity, inconsistency, breakdown. This raises a fundamental question. Are the glitches telling us about the universe or about ourselves? Are we discovering that reality is stranger than we thought? Or discovering the limits of human comprehension applied to cosmic extremes? The distinction might not be meaningful. Science is always an interaction between reality and observation. What we can know about the universe depends on what we can measure, and what we can measure depends on the universe's structure and our position within it. At the universe's edge, we're observing regions from which light has travelled for billions of years, stretching and redshifting through expanding space, arriving at our telescopes as faint signals barely distinguishable from noise. We're interpreting these signals through theoretical frameworks extrapolated far beyond where they've been tested. It's not surprising that problems emerge. We're working at the absolute limit of observational capability, making inferences about epochs we can never visit and conditions we can never recreate, using theories that might not apply at such extremes. Every anomaly we've discussed has multiple possible explanations. Impossible galaxies might form through unknown rapid processes. Impossible structures might reflect errors in our distance measurements. Redshift anomalies might come from systematic observational biases. Time dilation paradoxes might be artifacts of how we select and analyze data. The axis of evil might be a statistical fluke. Quantum breakdowns might reflect our ignorance of quantum gravity rather than failure of quantum mechanics. For each specific anomaly, conventional explanations exist that preserve standard cosmology with modest modifications. The field hasn't given up on the standard model. Researchers continue working within that framework, proposing refinements that might resolve individual problems. But the accumulation of anomalies is troubling. Each one might be explained individually, but together they create a pattern. Reality consistently misbehaves at cosmic extremes, violating predictions across multiple independent phenomena. This pattern suggests systematic problems rather than isolated errors. Either our fundamental cosmological framework needs revision, or we're systematically misinterpreting observations in ways we don't yet recognize, or reality genuinely operates differently at scales and epochs far from our local environment. None of these alternatives is comfortable. Revising fundamental cosmology means abandoning incredibly successful theories that explain vast amounts of data. Systematic misinterpretation means our observational techniques have hidden flaws we haven't found despite intensive scrutiny. Reality, varying with scale, means the universe is more complex than we hoped, with different physics at different scales. Yet one of these must be true if the anomalies are real. We can't keep finding violations of standard predictions without eventually accepting that something needs to change. The field is slowly moving toward this recognition. Papers discussing crisis-level discrepancies are becoming mainstream. Conference sessions address the impossible galaxies problem, the impossible structures problem, the Hubble tension, and other anomalies as serious challenges rather than minor puzzles. Younger researchers, less invested in the standard model, are more willing to consider radical alternatives. They're exploring modified gravity, alternative cosmology, and new physical mechanisms that might explain what standard models cannot. This generational shift in thinking is how science evolves. Established paradigms persist until accumulating anomalies force change. We might be approaching that transition point for cosmology, but revolution is not inevitable. Scientific revolutions occur when new frameworks successfully explain old problems plus new anomalies. Just recognizing that standard models fail isn't enough. We need better models that work. So far, no alternative framework has emerged that clearly outperforms the standard model across all observations. Proposed modifications solve some problems while creating others. The standard model remains our best available description of cosmic reality despite its issues. The way forward requires better observations and better theories developed in tandem. New telescopes will measure anomalies more precisely, determining which are real and which are artifacts. Better theoretical frameworks will suggest new observational tests to distinguish between competing explanations. This process takes time, decades possibly. We're unlikely to wake up one day with complete answers. Instead, understanding will gradually improve through accumulated observations and incremental theoretical advances. But certain truths are already apparent. The universe at its edges does not behave as our middle-range theories predict. Whether this reflects reality genuinely glitching or our understanding failing, we're confronting limits. These limits are instructive. They show us where we need to focus research. They reveal gaps in knowledge and weaknesses in theoretical frameworks. They challenge us to develop better tools for observation and better concepts for understanding. They also inspire humility. The universe doesn't owe us comprehensibility. It's not required to follow rules we find intuitive or beautiful. Our theories are approximations, useful in certain regimes but not necessarily valid everywhere. When we push to extremes, the very distant, the very early, the very large, our approximations break down. We shouldn't be surprised. We should be grateful that we've been able to understand as much as we have. The glitches at reality's edge ultimately remind us that science is an ongoing process, not a finished product. Each generation believes it's close to complete understanding, that just a few puzzles remain. Then new observations reveal how much we still don't know. We're in such a moment now. The standard cosmological model seemed nearly complete 20 years ago. A few details needed refinement, but the overall picture appeared solid. Then increasingly powerful telescopes began finding impossible objects and impossible structures. Now we're questioning foundations. Not because we want to, but because observations force us to. Reality at its edges is glitching, behaving in ways our best theories say it shouldn't. Whether these glitches are features of the universe or bugs in our understanding, they're telling us something important. They're showing us boundaries, not physical edges to space, but boundaries of knowledge, limits of theory, frontiers where what we understand meets what we don't. And beyond those boundaries lies mystery. Not mysticism or unknowability, but genuine scientific mystery. Phenomena we can observe but can't yet explain, patterns we can measure but don't yet understand. This is simultaneously humbling and exciting. Humbling because it shows how much we still don't know, despite centuries of astronomical observation and decades of theoretical cosmology. Exciting because it means there are still fundamental discoveries to be made, still revolutionary insights waiting. The universe is glitching at its edge. These glitches might eventually be explained by conventional physics with minor modifications, or they might require entirely new frameworks we haven't yet imagined. Either way, they're revealing that reality at cosmic extremes is stranger, more subtle, more resistant to simple explanation than we hoped. And in struggling to understand these glitches, we're learning not just about the universe, but about the nature of scientific understanding itself, its power, its limits, and its ongoing evolution toward deeper truth.